When someone says they optimized something, what are they really telling you? Is it really optimal or just better than before? Or just good enough? What techniques have they used to find the solution? Because that can tell you more about the quality of the solution or if there are rooms for improvement. And that's what we want to cover in this session. We will explore different solution approaches in optimization problems and how they can be used in decision making. When dealing with optimization problems, the two most common solution approaches are mathematical optimization, or MO for short, and heuristics. MO provides optimal solution, while broadly speaking, heuristics are designed to provide solutions fast for a specific problem with no guarantee on the quality or proof of optimality. It's true that both MO and heuristics provide solutions for the complex problems we try to solve, but they differ in several aspects, and each should have its own place in your toolkit. So, what are their main differences? The first difference is the solution quality. MO produces optimal solution, but heuristics don't guarantee optimality. Now, even if the optimal solution is not needed, you can still use MO to set the optimality gap or MIP gap. Now, what is this optimality gap? Briefly said, it defines how close from the optimal objective function value a solution can be to stop the optimization process. For example, maybe the lowest possible price that you can find for buying a used car is $10,000. Now, are you okay accepting a deal that has a listed price at $10,500? If that's the case, you're basically saying you're flexible and are okay accepting a solution with up to 5% worse objective value. Doing something like this is not possible with heuristics. The second difference is speed. When people talk about speed, they mainly refer to the execution speed or the runtime. Heuristics tend to have a faster runtime, but there is another speed to consider. How fast can the solution be implemented? Again, in this case, heuristics are usually easier and faster to implement as well, but there is an asterisk here. When the problem becomes complicated, developing custom heuristics can take even longer than writing MO. So take that faster implementation speed with a grain of salt. The next difference is scalability and maintenance. And mathematical optimization is easier to maintain and expand. MO captures the key features of the problem in decision variables, constraints, and objectives. So if any of those change, you can modify your model with the necessary adjustments easily, because the underlying mathematical programming engine and algorithms remain the same. For example, assume you are delivering some goods or products to customers and you're currently using a heuristic method. In your current objective is to reduce the total distance, but you see that the customers are not happy with your delivery and you start to lose them. You decide to increase the on-time delivery as well, making customers more satisfied. But the question is, how can you do that in your existing heuristics? These types of expansions and many similar ones can be handled much better using MO, especially when you have several and often conflicting business objectives. These are the major differences between MO and heuristic. Now, you may still wonder how to decide which one is the right approach for your problem. For that, we need to answer a few questions. The first question we need to ask is, how hard is the problem you're trying to solve? The answer to this is not as easy as it may seem, because you need to know your problem well. So keep a few things in mind. Number one, not all problems are created equal. Some optimization problems are usually more difficult to solve than others. And don't just think that the number of variables and constraints in a model is the perfect indicator of how long it takes to solve the model or whether it's solvable or not. Nowadays, you may be able to solve models with millions of variables or constraints in a matter of minutes. And at the same time, formulate a model with hundreds of variables and a handful of constraints and fail to solve it. Number two, even the same algorithm applied to different data sets of the same problem may result in completely different execution times. That means the algorithms you use or how you implement them matters. And that brings me to the third point, especially for those who may have tried MO and were disappointed by the results. How you formulate the problem can also have a big impact on the runtime. A famous example here is the cutting stock problem. If you're not familiar with it, simply put, the cutting the stock is the problem of cutting some rolls of materials like paper or sheets of metal into specific width to satisfy the demand while minimizing the waste or number of rolls used. For example, you may have rolls that each have a width of 20 units. Now you have certain demands for rolls of size 5, 7, or 9 units. Now, you can formulate this problem using binary variables, tracking usage of rolls, and whether a given demand is cut from a specific roll. But there is another way to formulate this. You notice that a roll can be cut into different patterns. For example, you can cut the roll of the 20 into 2 rolls of width 9. Or you can cut it in 2 rolls of width 7 and a 5. Or you can cut it in 4 rolls of 5, and so on. So, another way to formulate the problem is deciding how many of these patterns to use. Although both of these formulations will result in the same solution, they will have very different runtimes. So, formulation matters. Number 4, with the advancement in computational power and algorithms, some hard problems that could not be solved fast or not for a large instance can now be solved much faster. For example, consider the famous traveling salesman problem, or TSP. 10, 15 years ago, an instance of this problem with, let's say, 1,000 nodes could be solved in few minutes on your laptop. But today, the Concord TSP iPhone app can often solve instances of more than 1,000 nodes optimally, and all of that is done locally on your iPhone. And that's just one example. Companies were buying on-premise software and developers were running many of the models on their machines. The MO models were running fine on medium-sized problems, but they were getting into memory issues with larger datasets. And that was a big bottleneck and forced people to rely on some heuristics. But one other thing to consider is nowadays companies run their solutions on cloud. So you can easily spin up a larger machine if needed. And that's the fifth point. Memory is cheaper than talented resources. So if your main issue is memory, before you throw your hands up in the air, throw more RAM at the problem and see what happens. The next question is, how constrained is your problem? This one is related to the previous point, but it deserves its own discussion. When people think about the difficulty of the problem, sometimes they look at the many constraints they have and how hard it is to consider all of those in their current approaches, especially if the current solutions are based on heuristics. But unlike heuristics, more business constraints does not necessarily translate to a harder optimization model to solve. In fact, they may turn out a blessing in finding the solution because they cut down the solution space and leaving fewer options to evaluate. By the way, solving the model is different from writing the model. You may still need to write a model with many variables and constraints, but as we already talked about it, the number of variables and constraints should not immediately deter you. Now, let's think about an example that's familiar to many of us, and that's house hunting. Imagine you're searching for a new place, whether to buy or rent. Without any restrictions, you have all the houses on the market to consider. But as you start adding filters or restrictions like your budget, proximity to work, school, downtown, public transport, number of bedrooms, and so on, your options become fewer and the whole process becomes more manageable. Now, whether it's house hunting, planning a trip, scheduling shifts of different nurses in a hospital, or deciding on a location of a new distribution center, more restrictions may not be a bad thing. Next, you need to ask, how quickly do you need the results? Faster is better, sure, but do you really need to get your results in a matter of milliseconds or seconds? Or 1 hour is still an acceptable time? Maybe if you're solving a strategic problem every few years or a few times in a year, then even taking a few days to solve the problem optimally is more valuable than solving it in a few minutes using a heuristic. I remember a project where the model needed to be solved daily, and the runtime was more than 3 hours, and nobody could do anything during those 3 hours. So, on the surface, that was a terrible bottleneck. But in fact, it was releasing two resources that were doing all the analysis every day, and it was taking them the whole time. The moral of the story is, don't fret too much about the runtime if it's not the actual bottleneck. Another question to ask: how precise does the final solution need to be? Sure, you want to get the best solution, but how good is good enough? Is 1% worse than the optimal solution still acceptable? How about 5%? How about 10%? What's the gap that you're comfortable accepting? Of course, if you're deciding on the optimal level of ingredients in a drug, there should probably be no room for error and the solution should be optimal. But if you're making a multi-million-dollar investment decision, then a few $1,000s may not seem that big of a deal. Now, this is where someone may say, if not getting the optimal solution is acceptable, then why not use heuristics to get the solution faster? Well, remember, heuristics don't have a proof of gap. So you can't just say stop at 5%. That's doable with MO. Next thing to consider is, how are you currently solving the problem? Is this a new problem that needs to be solved from scratch? Or is it a problem with an existing solution? If the latter, what's the reason for exploring a different solution? Is it because the quality of the existing solution is not satisfactory? Or is it because the current solution doesn't scale well? Or are there new constraints or objectives that cannot be handled by the existing algorithms? Another important note here: if you currently have some system in place, maybe some heuristics, that provide you with a solution, but are not scalable or as efficient as you want them to be, and you prefer not to do a complete overhaul, then maybe you can combine your existing solution with mathematical optimization. For example, let's say you have a complex problem, but you're not happy with the quality of the solution that your current heuristics produce. So maybe you can use the current heuristics to quickly find a solution and then use MO to generate an optimal solution from that. Essentially, you're telling MO, don't start from scratch. I can help you. Here, take my solution and run from there. Or maybe a heuristic approach that decomposes the problem into a smaller, more manageable subproblems. And then MO can be used on each of those. And next, you can combine the solutions of each subproblem to get your final answer. So remember, it's not always either or. Mixing heuristic and MO is also an option. The last question to ask yourself is, how much time or resources can you invest in solution development? On one hand, if you have an experienced person, they can build an optimization model in a few hours or days, whereas the same person might require weeks to design and develop a custom heuristic. But the other side of the coin is that there are off-the-shelf implementations of some heuristics that someone with coding skills and with limited or no mathematical optimization background might be able to manage easily. Although, keep in mind that like many ML algorithms that have parameters, these heuristics usually require some fine-tuning as well, which is still critical. So far, we compared mathematical optimization and heuristics, and we talked about a checklist to consider when deciding which of those tools is more suitable for your problem. We can now summarize all that we learned into a couple of recommendations. First, consider the checklist. By answering those questions, I hope you gain a sense of where you can direct your time and effort for better results. Now, if after answering all the questions, you realize that getting the acceptable balance between the time and quality of the solution is still something that cannot be achieved through mathematical optimization, then consider using heuristic approaches. But keep in mind that heuristics and MO can complement each other and can also be combined together in solving the problems. Second, even if you opt for using heuristics, try to mathematically formulate your problem. This process alone can give you some insights into the problem's complexity, which is crucial when designing heuristics, because it can pinpoint the challenging constraints and perhaps spark some ideas on where to focus your effort when developing your heuristics. With all that said here, my personal rule of thumb is to first formulate the problem with the hope of solving it with MO. I know that because of the advancements in computational power and algorithms, the problem could be solved optimally, and this is a worthy investment. So if my model can be solved with MO, that's great. If not possible, then hopefully after going through the formulation exercise, I can design better heuristics. Now, at this point, you may ask yourself, sure, if I start building MO models, I still need an engine to solve them, right? And I hear more about commercial solvers like Gurobi compared to open source counterparts. But I have a data science background. And for ML algorithms, the difference between open source and commercial packages, in terms of quality at least, is negligible, if existent. Isn't that the case here too? Do I really need to use a commercial solver? Well, to answer that, we need a little refresher from Optimization 101. So let's briefly discuss the differences between open source and commercial solvers. As a reminder, mathematical optimization covers a few different technologies, but the most widely used of those technologies is mixed integer programming, or MIP. It is what we covered in Optimization 101 and continue to cover here as well. And I focus on MIP when I lay out the differences between commercial and open source solvers. The main strength of commercial solvers lies in lots of algorithms they have developed and their ability to exploit the model's structure. And the vendors have been continuously supporting and improving these algorithms over the years. Their dominance shows itself in several areas. The first one is performance, which is how fast the solver can solve your problem. Sometimes it's 1 minute versus 2 minutes, sometimes it's 1 minute versus 10 minutes, but it can also be 10 seconds versus 30 minutes. But it's not just about speed. Sometimes open source solvers may struggle with certain types of problems that commercial solvers can handle easily. So it's not just about the speed, but also whether my model can be solved. Then there is ease of use and available functionalities. Maybe you need support for specific platforms, APIs, cloud computing, and so on, which may only be available in commercial solvers. And the last thing is the reliable support. Because commercial vendors have full-time developers, a large customer base, and a big community, you can get your support much faster and better. But ultimately, your choice depends on your specific use case. If you have a straightforward problem, you don't need anything fancy or any functionality that's available only in commercial solvers, and open source solvers can handle it, then it's a no-brainer. Go ahead and use them. They're free and effective. But if you use open source solver and at some point it becomes unable to solve your problem, please don't jump into conclusion that your problem cannot be solved using MIP and you need to rely on heuristics. Before you go there, stop for a second and try your model with commercial solvers. And don't think that you need to pay them right off the bat. I'm sure all commercial solvers will provide evaluation licenses for free. This one comes from a personal experience. Several years ago, and when working with a client, I noticed they already have an existing MO solution, but they were using an open source solver. It was doing fine, but their problem size grew over the years, and then suddenly it was taking 25 to 45 minutes, depending on the data set, to get the solution. And that was really not acceptable for them. So one of the analysts there suggested that they should use heuristics. And that's when they brought me on board to help them with that. But honestly, all I did there was suggesting them to give commercial solver a try. They were surprised to see that their models were solving in less than 10 seconds. So don't give up too fast. Now, if after all of this, you are still struggling to understand this big gap between the quality of open source versus commercial solvers when comparing ML packages and MO solvers, then you probably need one last reminder. And that's the difference between ML and MO. We talked about them in Opti101, and we mentioned areas they collaborate and complement each other in solving problems. So I'll skip repeating all of those and only highlight an important difference between them. In ML, the core value is not in the ML algorithm itself. It's in the data you feed it and the computing power you have. However, in MO, there is a lot of value in being able to solve the problem. So the algorithms carry more weight. So at the end, it comes down to what brings the value. Yeah, Google or Meta open source their ML packages, but you don't see them open source their data. Well, with that in mind, I hope you now have a better understanding about mathematical optimization and heuristics as your optimization problem solving approaches. And you can use this knowledge to make the best choice based on your need. Thank you.